Yeah, so welcome to the Einsteinian revolution, context and implications of special relativity. My name is Jeff Fraser. I am not a physicist, but I loved physics in college, and I've continued to try to understand special relativity for most of my life, and I think I'm pretty close enough that I can explain it. How many of you have been exposed to special relativity in some form? Yeah, okay. How many are still somewhat baffled or confused by it? Okay, good. All right. Okay, good. So I hope that you read the course description, and I want to draw your attention to one sentence in particular. And that's the sentence in red. Yes, there will be equations. I hope, obviously, it didn't scare any of you off. It may have scared a few people off, but you're here. I want to make the math as understandable as possible. But the point is, you can't really appreciate the mind-boggling aspects of special relativity without the math. You have to see the math at least once to realize, okay, there is a mathematical basis for things like time dilation. Who's heard of time dilation? Right. Length contraction. So there's a mathematical basis, and it is completely counter to our intuition. And so if you don't see the math, it's almost not even believable. Okay. How about math? How many of you have had some exposure to calculus at some point? Okay, good. All right, I'm going to do it. We're just going to touch on calculus, but I'm going to present it as if you don't know any calculus. And interestingly, perhaps to you, is you don't need calculus for special relativity per se, but I do want to say a few words about Maxwell's equations, because this is a talk about the context, and you don't understand the context unless you understand something about Maxwell's equations. Or at least, again, just have a general idea. So a little bit of calculus, but not enough to disturb you too much. All right. Well, now let's just jump right in. If you recall, Einstein put forth two postulates. And from these two postulates, everything else follows. It is a classic story of deductive reasoning. It's like, okay, Euclid had a couple of postulates, and he developed Euclidean geometry from that, all of those theorems. Well, it's sort of the same thing. You just need two postulates, but you have to honor them. So the laws of nature are the same in all inertial frames of reference, and we're going to define an inertial frame of reference in just a second. And then second postulate, it is a law of nature that light moves with velocity c. What he's saying there is, doesn't matter which reference frame you might be in, you will measure the speed of light to be c. It's going to be the same for everybody. We'll, of course, get to that. So there's a lot to unpack here, and to do that, to unpack it properly, I feel like let's go back in history. And so today is going to be a little bit of a historical overview of the context. And then, as I promised, first we're going to define an inertial frame of reference. An inertial frame of reference is any reference frame or coordinate system that is not accelerating. That's it. So this train can be thought of as an inertial frame of reference, assuming it's not accelerating. So if it's standing still or it's moving with a constant velocity, it's an inertial frame of reference. So again, remember, constant velocity means it's not accelerating in terms of the speed or the direction. So it's moving in a straight line, constant speed. Now, I need to make a little caveat here. For the purposes of the discussion that follows in just a minute, we can think of the surface of our Earth and the air above us as an inertial reference frame for practical purposes. In truth, we're spinning around an axis, and we're revolving around the sun. So we are accelerating in that sense. But for short amounts of time, that amount of change in direction is so slight, it's not going to matter for our discussion. So just to be technically accurate. All right. Now, Einstein did not come up with this postulate himself. He was borrowing. It goes all the way back to Galileo. In fact, it is fair to say that if Newton is the father of classical mechanics, which is often said, then Galileo is the grandfather, without question. Some have called Galileo the first real scientist, the father of modern science in the general sense, not necessarily classical physics, but in terms of the experimental method and so forth. So Galileo is very important to science, but in particular to our story today. And before there was special relativity, there was Galilean relativity. So let's now just briefly explore Galilean relativity. And this is from Galileo's own writings, the little story I'm going to tell you. It's a thought experiment. Maybe he did this in reality, but in his writings he presented it as a thought experiment. And as you may know, Einstein, that was one of his most powerful tools, was the thought experiment. So Galileo says, consider a sailor up in the crow's nest. The ship is moving with uniform velocity of 10 feet per second. So if he drops a ball from the crow's nest, let's say a heavy ball, lead ball, where does it land? Aristotle, going back to the ancient Greeks, he would say that because the ship is moving, the ball will land some distance from the mast towards the stern, like this. And Galileo says, no, that's wrong. It will land right at the bottom of the mast, just like that. And okay, so let's explore that idea a little bit. So let's say the duration of the ball's fall is 4 seconds, and let's say we are now standing on the shore watching this event. And so the following is from our perspective on the shore. The ship is still moving at 10 feet per second to our right, and these little, this coordinate system is to show you distances in increments of 20 feet. And remember, the ball, it takes 4 seconds for the ball to fall. And we see that the ship has moved 40 feet to the right, and so has the ball. But as a result, the ball lands at the bottom of the mast. Now, if we want to imagine the trajectory that the ball follows from our point of view, it follows half a parabola, and that's because there's acceleration. And Galileo knew about trajectories because he was interested in projectiles and so forth. We're not worried about gravity or acceleration, but that's just to be complete. The point is that in terms of the horizontal motion, this is an inertial reference frame, and the ball moves in sync with the ship itself. No mystery there, although Aristotle would have argued with you. Now let's say the sailor tosses the ball towards the bow at a velocity of 10 feet per second. So the ship's moving 10 feet per second, and now the ball's moving on top of that. Now these coordinates now represent the sailor's frame of reference. So after 4 seconds, he sees it only move 40 feet. But on shore, you can guess what follows next. On shore, we see it falling 80 feet. And the point of all this is that velocities add in a very straightforward manner in Galilean relativity. That's all it is. Velocities add in a very straightforward way. And in this case, the velocity of the ball in the shore frame equals the velocity of the ball in the ship frame plus the velocity of the ship in the shore frame. Now that's a mouthful, but I think you get the idea. But I want to show you one very dramatic demonstration of Galilean relativity to a first approximation. And I think the grand wizard in the Instagram cloud somehow knew that I was studying special relativity, so it sent me something in my feed that is a demonstration of Galilean relativity. So let me set this up for you. What you're going to see is, let's see if I can do this. Here's a truck. This truck is moving towards us at a speed of 80 kilometers per second. No, 80 kilometers per second. I'm getting ahead of myself.
Wow. Rocket truck.
80 kilometers per hour, excuse me. I'm thinking of something else already. I'm thinking of spaceships that we're going to show you later. Okay, 80 kilometers per hour. Now, this truck has a very long flatbed in back. Okay, you can't see it yet. And on this flatbed, close to the cab, but facing away from the cab, is a man sitting on a chair, right up against the back of the cab, and he's facing towards the back. And this is a very special chair. It's hooked up to some sort of fancy accelerator or catapult or slingshot, whatever. What's going to happen is they're going to hit a switch, and it's going to send them in the opposite direction and accelerate him. So by the time he is ejected from the chair at the other end of the flatbed, he will be going 80 kilometers per second, kilometers per hour, in the opposite direction. Well, I think you can guess what you're going to see here. Whoops. Okay, now I have to go. Oh, okay, let's see if I can do this. Let's see, I have to go up here. Let's see if it'll work. No, it doesn't work. Darn it. Well, you can guess what happens. The problem is I've got my main display on my computer and an extended display up there, and I can't control the video.
Can you demonstrate that?
Well, I can give you the bottom line without actually demonstrating.
You need to make your computer move.
Yeah, right.
Throw the computer.
Well, you see him accelerate, and sure enough, he ejects from the back of the flatbed, and from the point of view, the camera I think is attached to the truck, so it looks like he's being shot out this way, but from land, he's motionless in air, and then he just falls straight down. Lands on his feet, sticks the landing, as they say. All right, so you get the idea.
Only a few broken bones.
Yeah, no, he was perfectly fine. All right, so Galileo's interested in the motion of bodies. And one of the reasons he's interested in moving bodies has to do with this guy, Nicholas Copernicus. So this is about 70, 80 years, 60, 70, 80 years before Galileo starts getting interested in all this. So Copernicus had published a book on the revolutions of the celestial spheres. He saw the first published copy of this on his deathbed, which made him very happy to see it was published. And in this book, he describes a heliocentric cosmos. And this was a radical departure from the accepted wisdom of the ancient Greeks, the geocentric model, the Ptolemaic model. This is a very radical proposal. And one of the reasons it didn't get published sooner is he was kind of waiting. I think he was concerned that he might get in trouble with the church or be ridiculed by fellow scientists because this was such a radical idea. And in fact, it's maybe striking in hindsight that his model was not accepted for 100 years or more. There was ongoing controversy because, to be fair, his model was not perfect yet, had not been perfected by followers, and it was not necessarily any better at predicting the motion of the planets compared to the Ptolemaic model. And that's partly because the Ptolemaic model was pretty good. It had been finally honed by the Greeks and gotten to be very accurate in terms of predicting where the planets would be relative to the stars and so forth. So anyway, that's a whole separate, very interesting story. And this debate continued. Now, Galileo came along and he invented a telescope. He didn't invent the telescope, but he perfected it. It had just recently been invented by a Dutch scientist, but he got a hold of the plans and he worked on it and improved it. He was actually the first one that got it to the point where it was the resolution and the power was enough that you could actually study the planets and so forth. And he did that, and based on some of his observations, he was convinced that the heliocentric model was the correct model. Now, people, even though he published that finding, people still were some people were still skeptical. So you had two camps. Kepler was in the camp of Copernicus, and of course, eventually the Copernican model won out, although it had to be modified. Again, that's a whole other story. But the point is, the interesting point is, not only was Galileo convinced that the Earth went around the sun, he believed that it must be the case that the Earth revolves around its axis every 24 hours. Why? Because of course, everything rises in the morning or rises in the east and sets in the west, whether it's the stars at night or the sun during the day. And so everything's moving around us every 24 hours. And the ancient Greeks said, well, that's just because that's a different substance and it's light or it doesn't weigh anything, so it's not that big a deal to move it around. And Galileo says, that's too complicated. The Earth revolves around an axis. Well, that was also contrary to the Ptolemaic model. And one of the arguments against the Earth revolving was simply the common sense argument. If the Earth was rotating, we'd notice it, we'd feel it, but we don't feel it. We seem to be standing still. So Galileo, again, this is his ability to think in unconventional ways and to consider unconventional and unpopular explanations. Now, his adversaries would say something else. They would say, Galileo, when you drop one of your balls off the top of the Leaning Tower of Pisa, which we don't really know whether he did that in fact or not, but he certainly was aware of that kind of experiment. He said, they said when you drop your balls off the Leaning Tower of Pisa, they drop straight down and land right near the base of the tower. And if the Earth moved, as you say it does, the ball would land some distance from the tower. Well, that was just what he was talking about with his crow's nest and the ship experiment. He would say, no, you're wrong. What is going on is the ball's in an inertial reference frame with me. We're all in the same inertial reference frame. And the laws of physics say, no, it's going to fall straight down in our reference frame. Yeah, just like the sailor. So Galileo publishes his beliefs, his proposals, his theories in a work. It was The System of the World in 4 Dialogues. What he does here, this was kind of his, the genre that he liked. He loved dialogues. So what he does is he writes a book that consists of dialogue between 3 fictional characters, debating this whole issue. Now the author's avatar is a character named Salviati, and Salviati, of course, is in favor of the Copernican model, and his argument is convincing. Wins the day, according to the way the book winds up. And for all of this trouble that he went to, maybe you know what happened to Galileo. He was brought before the Spanish Inquisition. He was convicted of promoting heresy, and he was sentenced to house arrest for the rest of his life. So he did something that was actually sort of dangerous to do back in that day. So we're not quite done with Galileo, but what I'm going to start talking about now, we've talked about Galilean relativity. Now we want to talk about the speed of light. That's also part of Einstein's postulates. And I thought it would be interesting, again, to be complete about the context of special relativity. What is the speed of light and how did they discover it? So it's an interesting story. I hope you enjoy this. Let's go through it. Galileo was interested in the speed of light and he tried to measure it. And he came up with this following experiment. So one night, standing on a hilltop, Galileo uncovers his lantern. His lantern has a cover on it. He uncovers it. And he has an assistant on top of another hill, some distance away. And the assistant is instructed to uncover his lantern as soon as he sees the light from Galileo's lantern. And then Galileo will in turn see the light from his assistant's lantern, and he has to note the time. Well, you can imagine the problems, but one of the big problems is back in the day they didn't have very accurate clocks. The only thing Galileo had to measure time was a pendulum, not a pendulum clock, just a pendulum, his pulse, or a water clock. They had water clocks back then. None of these are terribly accurate. So Galileo couldn't get any good answer, and he concluded that the speed of light was simply too fast to measure. So that was the first part of our little story today. The next part of our story has to do with this guy, an English astronomer named James Bradley. the year is 1725. So Newton has already published his Principia 50 years earlier. But still, there's some desire to identify or prove something called the stellar parallax. And we'll get to that in a minute. I'm going to tell you what the stellar parallax is. But as far as the speed of light goes, up to this point now, 1725, now we're 100 years after Galileo, there had only been one somewhat successful attempt to measure the speed of light. 50 years earlier, a Danish astronomer, using some astronomical observations related to the moons of Jupiter, came up with an estimate for the speed of light that was not too bad. It turned out it was about 25% too low, but it was a start. Anyway, here's the first reason why I like this story. James Bradley was not interested at all in the speed of light when he took up his enterprise. Again, what he was looking for was the stellar parallax, or an example of, or proof of that the stellar parallax exists. The stellar parallax refers to a shift in the apparent position of a particular star. In theory, it would have to be what we might call a foreground star. A star that's much closer to Earth than most other stars. And so I think you can see the idea here. If you look at this particular star at a point in time, say December, and then 6 months later look at it again, if the Earth goes around the sun, one should see a change in the angle. And the way you would measure the angle is basically by seeing how that star lines up with the background stars. Simple enough. If you still want another example, it's a simple matter. You can hold up your index finger and cover one eye and look at me. And then if you cover the other eye, of course, the finger moves sideways. That's parallax too. So the point is that there were still a few people who questioned the heliocentric model, and they said, nobody's been able to show a stellar parallax before, but if the Earth goes around the sun, there has to be a stellar parallax. And Galileo's rebuttal was, well, the stars are all too far away. We just don't have an instrument accurate enough to measure such a tiny shift in angle. But that was Bradley's ambition. And so Bradley's attention is focused on a star known as Gamma Draconis. It's in the constellation Draco, shown there. And there were a couple of reasons why he was so interested in, I'm going to call it Gamma D. Gamma D. Number one, it's a bright star, relatively bright star. In fact, it's bright enough that you can see it with the aid of a telescope during the day, and that's unusual. And so that suggested, the fact that it's that bright suggested it's probably closer to us than other stars. So it would be a good candidate for stellar parallax. The second reason he was interested in it was that, as it happens, once every 24 hours, usually during the daytime, it will be visible directly overhead if your observatory happens to be in London. That's just an accident of nature. This particular star is almost directly overhead once a day in London, of course, with a telescope. Now, why is that important? Well, he wants to get a very accurate measurement of its angle, because it's not going to be directly overhead. It's going to be deviated a little bit, just a fraction of a degree. And he was worried about refraction. So the atmosphere will refract light from stars, but if the light's coming from directly overhead and almost perpendicular to our atmosphere, the refraction is almost negligible. So this is a great idea. Let's see how it played out. So one of the first problems was, because he's looking at it during the daytime, he's not going to have those background stars to look at. So he needs a very, very precise instrument, a telescope where you can measure the degree of deviation from true vertical to within a very tiny fraction of a degree. And so he needs a master craftsman to construct this telescope, and he finds one. I don't have the name in front of me, but he was one of the best telescope manufacturers at the time. The telescope, here's the drawing. It's 24.5 feet long. And it's called a zenith sector telescope because it's really not meant to deviate from vertical very much. But when you do want to deviate it, you can deviate it down to a tiny fraction of a degree. There. So he's got something he thinks is going to be the tool he needs. The original telescope, interestingly, was lost, but he had a modified version that survived all these years, and it is now on display at the Royal Observatory. So if you're in the neighborhood. Okay. So just to refresh your memory, the Earth goes around the sun, and the axis is tilted, and that causes our seasons. So for the purposes of our model and our discussion, we're going to be very interested in 4 points in time: winter solstice, summer solstice, and then spring equinox, autumn equinox. And the other thing to know is that by 1728, astronomers had a pretty good idea of the distance of the Earth from the sun, and that was helpful. And that's not an easy thing to measure, by the way. That's a whole other story. But anyway, they knew approximately the distance from the Earth to the sun. That allowed them to calculate the length of its orbit, elliptical orbit. And when they knew the length of the orbit, and they knew that there are 365.25 days in a year, they could figure out the speed of the Earth approximately. So the speed of the Earth is 30 kilometers per second. So now that's faster than the truck, a lot faster. 30 kilometers per second. We'll see why that's helpful in a minute. Okay, so now we're going to talk about this model. And I want to reintroduce you perhaps to spherical coordinates. Very simple. We use spherical coordinates when we talk about positions on our globe. So you've got longitudes and latitudes. That's it. And the equator is 0 latitude. And so latitude is perhaps 40 degrees north or 40 degrees south, and so forth. Okay. So here are the 4 Earths. White for winter, dark red for autumn, green is spring, and blue is summer. Here's the sun. And here's little Gamma Draconis, or Draconis, way up there. But of course, this is not to scale. So you have to imagine Gamma D, 150 light years away is how far away it is. So the point is that, and it's actually probably as big as our sun. So the light rays coming from Gamma D, when they reach our solar system, they're virtually parallel. That's one point. So you think of those light rays coming down from Gamma D as virtually parallel. And as I said, at each of these points in time, this telescope's pointing more or less vertical for London. But Gamma D is within his sights, and then he can line it up and measure how far it deviates from vertical. And he imagines, stellar parallax being his whole purpose, he's going to see that angle changes slightly and gradually as he goes around the sun. The other point is, in terms of our spherical coordinates, just by convention, when the Earth is at the autumn equinox, that's 0 degrees longitude. Then we have 90 degrees longitude, 180, and 270. The other thing that's kind of convenient for telling the story is that Gamma D is 270 degrees longitude. So the longitudinal line would be coming down like this, or out there like this. So it's sort of right above the Earth and summer solstice.
What?
Did I lose somebody there?
Yeah.
Okay.
I mean, it's not going to be right above the Earth because it's off.
Well, of course. Right.
Like 57 degrees
right.
latitude, something like that.
It's actually at 65 degrees latitude.
Okay.
But you're right, it's going to be way up there. So it's going to be way beyond. I said that wrong. It's simply the right way to say it. It's the same longitude as Earth would be during the summer, but its latitude is 65 degrees. By definition, the Earth is always at 0 degrees latitude because the ecliptic plane is like the equatorial plane. Thank you. Right. So it's not right above Earth. It's way over here. And that's why, again, you can't build a model of scale. So this is my attempt. All right. So let's see. What else do I need to tell you about this? Okay. Okay, so Bradley predicts that the parallax will be more pronounced when he comparing observations spring equinox versus autumn equinox. That's going to show the maximal stellar parallax. He will still see a parallax comparing summer with winter, but it won't be as much. So let me just show you why, because again, might as well make sure we're being rigorous here. So these rods are to show you angles. So here's the angle for spring and autumn. Okay, I think you can kind of see what that is. Now notice that angle would be, let's say that gamma d was right over the North Pole. This is the North Pole of the ecliptic coordinate system. It would be the same. The angle doesn't change regardless of the latitude of gamma d. Now, if you look at the parallax here, the angle may not look that much different to you. And again, you can't really measure it because it's really way over here. But just the point is this: I don't have to. I can just say a couple of things to convince you. Again, imagine gamma d was over the North Pole. This angle, gamma d is over the North Pole. This angle would be the same as this angle. However, if gamma d was down here, whoops, the angle would be, whoops. Oh, it's all right. Oh,
Sorry, star.
Got sucked into a black hole.
Yeah. Anyway, if gamma d was down here, the angle would be almost 0. So, as the latitude of a star, let's say any star, if you can imagine a star migrating, in this arrangement, the stellar parallax would be close to 0 down here, and it would be a maximum up here. So it's somewhere in between. So it's less. The point is simply this, and this is why I think the story is so interesting. Bradley noticed that there was these angular deviations, so maybe there is a stellar parallax. But to his credit, he said, but wait a minute, I was certain that the stellar parallax would be greatest between comparing autumn and spring. But that's not what he found. He found that the parallax, or no, excuse me, not the parallax, but the deviation was greatest between summer and winter. And that was the key. And he said, you know what? I'm not seeing the stellar. He was convinced. And again, to his credit, he could have just published it and sort of fudged the data and said, here's your stellar parallax. Thank you very much. No, he didn't do that. So he's a good scientist. So the shifts were maximal in exactly the orientation that he did not expect. And just want to make sure we take a break. We'll take a break in a few minutes. So he's thinking things through. Stellar parallax does exist. It is a real phenomenon, but you need instruments even more precise than his to see it. So years later, decades later, I'm not sure how much later, maybe 100 years later, they finally did prove that this star, you can demonstrate stellar parallax, and one of the reasons you can do that is because it's relatively close. So his idea was completely valid. It just, he didn't quite have a strong enough telescope. But he did find something. And so, again, if it was truly a geocentric cosmos, you shouldn't see any angular deviations, unless the star itself is moving, which was again foreboding. These are fixed stars; they don't move around. That was part of the faith. Okay. So I hope you're still with me. Let me explain the answer. What?
Presumably fixed stars are moving, they're just not moving in relation to us, right?
Well, that goes back to a minor problem with the Ptolemaic model. The Ptolemaic model says, yeah, the stars move. They go around us one revolution every 24 hours. So yes, but they're embedded in a sphere, so they don't move relative to each other. And the other thing is, they always wind up in the exact same position 24 hours later. Again, there's a little bit of handle. Yes?
Isn't the reason for that the distances are so vast in comparison to the velocities that you don't see the movement?
Oh, now we're talking about something else entirely.
Yeah, but that's
the
why
universe
you
is
don't perceive
expanding.
them moving.
Yes, the universe is expanding, so the stars are moving. And in fact,
Well, they're moving relative to each other. But
yes.
you know, if you're 50 light years away and you're going 100 miles a second, you're not going to see that motion.
Right.
In a person's lifetime, usually.
That effect is more minuscule still. So it's a good point. The stellar parallax effect is more robust than that effect, and so. For the purposes of the discussion, you can assume that the stars are still more or less fixed, but they're not. We now know that. All right. So I found that his understanding of the actual explanation was fascinating, so bear with me. And then after I finish this, we'll take a break. So the answer to this conundrum is raindrops. So Bradley starts thinking about raindrops. So here's a game. Let's imagine you're holding a tube and it's raining. And somehow you know that the raindrops are falling at a speed of 20 kilometers per hour. And the game is this. You want to hold your tube steady and straight so that any raindrop entering the tube on top falls all the way through without touching the sides. In theory, that's very, very simple. You just have to hold it true vertical. But wait, what if you're walking 5 kilometers per hour to the right? What do you have to do here? Do you have to tilt the tube? Think about it. But but the easier way to think about it is to again use Galilean relativity. Remember I think Galileo did say this. If he didn't, it was implicit. Galileo would say if you have two different reference frames, because they're moving relative to each other, to call one frame the rest frame is simply a matter of convenience, or to make it easier to do your calculation. So you're always free to change what you think of as the rest frame. So to solve this problem, what we do now is we imagine that the wind is blowing. You're standing still, but the wind is blowing 5 kilometers per hour the other way, and it's blowing those raindrops to the left. So they're falling down and moving to the left at the same time. So again, you're going to have to tilt your telescope to the right. But if you know the data, you can even calculate how much you need to move it to the right. This is a little trigonometry, or trigonometry. Here's the vertical velocity down, and here is the horizontal velocity. And this is vector addition. This is velocity. This is adding velocities. We talked about adding velocities. Well, sometimes you add velocities because the velocities are going in the same direction or against each other. But you can add velocities at various orientations. And thanks to the right triangle, if they're going perpendicular to each other, you can use trigonometry. So what's the angle here? That's what we want to know. That angle is, the tangent of theta is 20 divided by 5 is 4, and so you go to your trig tables or to your calculator. All right, we know that angle is 76 degrees. So that's how much you'd have to tilt your tube. Okay. Okay. Now let's go back to our model for a minute. And let's look at, what did I want to do? Winter solstice. Okay. So, winter solstice, here are the light rays coming down from gamma D, and the Earth, at this particular moment in its orbit, is moving at a perpendicular direction from the light rays. Okay, so I think you can see where we're going with this. The black rectangle here represents its telescope. What is a telescope? It's basically a tube. And with reference to light, it's open at both ends. Okay? So that's the whole point here. Bradley finds that he has to tilt his telescope a little bit to see the light. And we're going to be talking about light primarily as waves during this talk, right? But it also has particle characteristics. And we'll talk about that. But for now, think about light as particles. Newton would call them corpuscles. Newton thought they were corpuscles. They were little particles. We call them photons. So imagine, okay, so the photons are coming down, and we're moving to the right. But that would be the same as if the photons were moving down with the speed of light, but also to our left at 30 kilometers per second. And we're back to a trigonometry problem. The difference is we don't know what C is, but he's just measured theta. His telescope was useful in that sense, and he found that the angle theta was 89.995 degrees. Pretty close to 90, but not quite. And so, what's the tangent of theta, of this theta? Well, you can figure out the tangent of this angle, and from there you can figure out, oh, well, okay, C divided by 30 is the tangent, so you solve for C, and lo and behold, he gets an answer. 301,000 kilometers per second, or 301 million meters per second. Now, if you know the speed of light already, you can appreciate that's remarkably close. So this was really a very neat experiment, and that's why I had to tell you the story, because it surprised me, but I thought it's interesting in its own right, but it brings in Galilean relativity and adding velocities. And here he is, he's trying to demonstrate stellar parallax, and he fails. But in spite of that failure, what does he do? Well, he demonstrates what was called the aberration of light. And it's not really a property of light at all. It's simply the phenomenon that occurs if you're moving perpendicular to the direction of the light rays coming down. You have to tilt your telescope. So the aberration of light. And so, but it accomplished the same goal in a sense. Whether he found stellar parallax or the aberration of light, he proved that the Earth is moving. That's what Galileo famously said. He said the Earth moves. And so we have Galileo's observations, and now we have Bradley's findings. This was probably the final nail in the coffin of the Ptolemaic geocentric model. And on top of that, as an added bonus, he discovers the speed of light. It's remarkable. All right, well, let's take a short break, maybe 5 minutes, and then we'll come back again. I'm hearing something here. So we've got a pretty good estimate of the speed of light now. So just remember that one number, about 300 million kilometers per second. 300 million kilometers per second. That's moving.
Who are you?
300,000 kilometers per second, or 300 million meters per second.
Yeah.
All right. Again, I always had problems with units, going all the way back. 300 million meters per second. Okay. After Bradley's work, maybe a little bit more than 100 years later, a couple of scientists succeeded in getting a pretty good measure of the speed of light using a land-based method. And remember Galileo and his lanterns? Well, they used some more, they kind of updated that idea. I won't go into that. I will tell you this: what I've done in the past is export my entire presentation to a PDF file, complete with photo, pictures, and so forth. If anybody's willing to punish themselves that much, we can make that available. But really, what it would be for is if you thought of one particular point of the presentation today and you said, I want to review that. Well, you're going to have to go through a lot of stuff you don't want to review, but you'll find it in that PDF file. Yes?
Bradley didn't have meters in those days, did he? What unit did he use?
Oh, right. I translated it into, obviously, meters per second. What was it? Did they use feet back then? I don't know.
Miles? Did they?
Well, certainly miles, yeah.
But was there any standard? There must have been some standard.
And I don't know if the mile had been standardized at that time. I don't know. Good question. That did not come up in the source that I read. So. All right. But anyway, so we're going to move on. We've got an idea what the speed of light is, and we're going to be talking about light in terms of waves. And you've probably been exposed to the mathematics of waves at some point. But again, I'm not going to assume anything. Let's just go through it. But to start off, let's talk about sound waves, because that's a little bit easier. And sound waves will ultimately prove to be the perfect counterexample to light waves, as we'll see. So you have a speaker. If you know how a speaker works, it's very simple. It has a diaphragm. There's a wire coil in there that creates a magnetic field, and there's a metal piece. And as the field oscillates, the diaphragm oscillates. And so what does that do? All it's doing is pushing on the air and pulling on the air. It's compressing the air and then creating a vacuum. And so for the purposes of our discussion, let's imagine that this speaker is programmed, or the signal that it's receiving electrically will produce a perfect tone A, a perfect musical note A. So we know what the frequency is. The note A, as I learned, is 440 cycles per second. I believe that's the standard tuning for it, right? Okay. Now, a sound wave generally spreads out in all three dimensions, but obviously a speaker has a particular favored orientation. So let's just assume that the sound wave is moving through a tube, or even imaginary tube, in this one direction. And the red represents high pressure, blue represents low pressure. So you're seeing the oscillation, and it's a gradual change from one extreme to the other. And the white would be what you could call the node. That's where the pressure normalizes for a brief, that's normal air pressure. So it's oscillating above and below ambient air pressure. That's a sound wave. And the way we're going to construe this is to say, if you took any cross-sectional area through that tube, the pressure would be the same in that entire cross-sectional area. So again, here's just showing. Here's the cross-sectional area. You look at the cross-section, it's all the same shade of blue. That is a plane wave. Here it's all white, and there it's all red. It's a plane wave because in that cross-sectional area, cross-section, the amplitude is uniform. Well, that's a plane wave, and that's an important concept for our discussion. And so now imagine that we're going to sample the pressure everywhere in the tube along this green line. Well, at first we're just going to pick out certain points. But this green line, we could make that the x-axis. And then the y-axis is going to be the pressure. And I make this point because when I used to look at light waves and try to figure out what's going on, it was very hard for me to remember, well, when we represent the air pressure along the x-axis, it's going to be a sine wave. And so as I was saying, when I looked at light waves, I would always get confused because I want to see the y direction as the spatial direction. But as we shall see, that's the y direction could be the electric field or the magnetic field. In this case, it's the pressure. So we're really looking at the pressure along a single dimension. However, because it's a plane wave, it wouldn't matter which horizontal horizontal line we use. It could be any horizontal line within that tube, and the wave that we record is the same. Again, that's what it means to be a plane wave. Now, every wave has three variables. It has a wavelength. It's the length of one complete cycle. It could be from the deep blue to the deep blue, or the deep red to the deep red, or from the node to the node. Well, actually, from one node to the second node from there. So it's easier to do it from one maximum to another. And frequency, of course, refers to the number of full cycles that pass by a particular point in a particular reference frame. That's the frequency. And then there's the velocity. And the velocity of sound is more or less constant at a given temperature, at a given air pressure, and so on and so forth. Let's say 343 meters per second. And there's an equation that relates these three variables. It's simply velocity equals frequency times wavelength. And that makes sense. A wavelength is one cycle. It has a certain length. And if you have 60 of those cycles per second, you're going to get 60 wavelengths per second. Something like that, or 440 wavelengths per second. So knowing the velocity of sound and knowing the frequency, we can calculate the wavelength if we want. And it's about 0.78 meters. Okay, just as an example, just to get you comfortable with these little equations.
So, can I
Yes.
ask a question?
Yeah.
So the 0.78 meter is the distance between peaks, is that what that means?
Well, that's what I was trying to explain. It's the difference. It's the length of one cycle. So it's the difference between this peak and this peak, but it can also be the difference between that peak and that peak, or it could be the difference between this node, not this node, but the second node, because
Has to go through the whole thing. Okay, good, thank you.
that's a wavelength. Okay, now imagine that I'm skating away from the source of the sound at 20 meters per second. Now, if I could skate that fast, I would have been in the Olympics. I can't, but it's a thought experiment. So I'm allowed to skate that fast. So now, relative to me, the velocity is 20 meters per second less, so 323 meters per second. Okay. Now, one thing about sound waves, the wavelength is the wavelength within the medium that's carrying the wave, and that's a rule. If you ask me, well, you're skating away, what's the wavelength? Well, it's the same wavelength. So, in this setting, the velocity changes, the wavelength is constant, so what happens to the frequency? It goes down as well, and that's the Doppler effect. So if you're familiar with the Doppler effect, that A will no longer sound like an A. So very simple. And the new frequency is 414 hertz, if you want to do the math.
Fascinating.
So a sound wave is a traveling pressure wave. And the amplitude at any point represents the difference in air pressure above or below ambient air pressure. Oh, I know what I was going to say. I don't want to get too hung up on amplitudes when we start talking about light waves. So if I don't show you an amplitude, just assume it's 1, because you can always call it 1. You could just have a conversion factor that gets you back to whatever your normal unit is. We'll get to that, but I just want to sort of warn you ahead of time. If you say, well, what's the amplitude of that wave? Well, I'd say, don't worry about it. Yes.
So just a question, you showed the skater
Yes.
moving at 20 meters per second.
Right.
But the sound source could also be moving, right?
Yes.
And that I think is the one we experience all the time, isn't it? When we hear
Yes.
the sound get lower,
Right.
get higher when something approaches.
Right. So to your point, when you experience the Doppler effect, it's not usually because you're moving, it's because the source is moving.
Yeah.
But there is a reciprocal relationship.
That's interesting.
You can also have changes created by wind. I didn't want to get into all of those variations. You're absolutely right, but for the purposes of our discussion, all we have to worry about, we're going to be assuming that the source is in the same reference frame as the medium for our purposes. So that's a good point, though. So the source and the medium are in the same reference frame, but the observer might be the one who's in that frame or in a different frame. Good point. Okay, so we've got this sine wave showing the amplitude of pressure over a stretch of space. And in this frame, of course, time is frozen. If time were not frozen, the wave would be moving, let's say, to our right. But I wanted to freeze time, just to remind you, okay, here's the wavelength, 0.78 meters. And notice that the pressure is 0. Again, this is called the node. It's 0 here and here. This is half a wavelength, right? So every half wavelength, the pressure becomes 0. And from that knowledge alone, if you don't worry about amplitude, you can construct an equation for this wave with time frozen. And it's simply to remember that we're dealing with sine waves. If you want the pressure to be 0, well, you have to have the sine of 0 or the sine of pi or the sine of 2 pi or 3 pi. Any integer multiple of a half wavelength will give you 0, which is what you want. So your equation has to agree with that. And so you can write it out like this. Pressure equals the sine of 2 pi x over lambda. What's going on here? Well, if x equals lambda, just as a simple example, that cancels out and it's 1. So then you just have the sine of 2 pi, which is 0, which is what you want. So again, not to beat a dead horse, but we know the wavelength, and so if x is a multiple of this, or even a multiple of half of that, this will turn out to be some multiple of pi, which means the sine will be 0. And I say, technically I could put an A. This is where the amplitude shows up, right in front of the sine function. But let's just not worry about amplitude, just think of it as 1. Now, time is still frozen, but we're looking at the pressure through this little window. And we're going to unfreeze time, and as we unfreeze time, that wave is going to be moving to the right. But that would be the same as what? Time is frozen, but our window is moving to the left. And this is how we think of frequency for the moment. And so if we start at that point, which is 3/2 of a wavelength, I'm just showing you. Okay, so our window is going to move to the left at the speed of light. And I think that should be 343.
Yeah.
That's all right.
Just a skater.
Yeah. Yes, right. Okay, so there's one wavelength every 1 over 440 seconds. And that would take us one wavelength over where it's 0. So we need our sine function to be 0 when our time window is moving for that length of time. So here's our expression from before. Then we have to add on the other variable, time. And we do that by subtracting minus 2 pi f frequency times time. So if the time is, if the frequency is 440 cycles per second, and we travel in our window 1 over 440 seconds, Again, this cancels out. We're left with 2 pi. Long story short, we would wind up at a half a wavelength from the origin, and that would be sine of pi would be 0. So if that's kind of confusing, that's probably the most difficult part of this. But the point is, this is the standard equation for a wave, and it's going to be relevant when we talk about light waves as well. All right, so there's a mathematically correct way of expressing a traveling wave. A traveling wave means what? The amplitude is a function of space dimension, but also of the time dimension. That's all you really need to remember. Okay. So now a little mathematical interlude. And this will be a good way to wind up.
Yeah.
Your brain will be fried, but you'll be all ready for Maxwell's equation next time.
Oh, yeah.
And that's just going to be mind-blowing. So absorb this, and then you can relax for a week, and then we'll come back. Okay. So again, you've had some exposure, many of you, to calculus. Let's just talk about it in a very simple, intuitive way. All right. So here we go. Let's imagine there's a car driving down a straight highway at a constant velocity, and at time equals 0. At time equals 0, it's at some arbitrary location in the x dimension. The nice thing about special relativity is we don't really ever have to deal with 3 dimensions, really. It's just 1 dimension in space and the time dimension. So that makes it easier. So the car's traveling down the x-axis, if you will, over time, and this is what it would look like at constant velocity. It's a straight line. We could say that x is a function of t, or distance is a function of time. And when we talk about velocity now, well, what's the velocity? Well, we can talk about average velocity. Let's talk about average velocity. For average velocity, you just take some arbitrary interval of time, and you ask, well, how far did the car move during that time? And you divide delta x by delta t. Delta x, delta t, that just means a change in that particular variable. So that's going to give you average velocity, whether it's a straight line or not. But as it happens, because this is a straight line, the average velocity is also equal to something called the instantaneous velocity. Instantaneous velocity is the same because velocity is constant. And now if we're going to use the notation of calculus, we're just going to introduce a little notation here. We say v equals dx dt, and so instead of delta x and delta t, it's dx and dt. That just tells you right away that we're dealing with calculus. We're dealing with infinitesimal changes, and that's really one of the groundbreaking things that Newton did was to cope with this kind of thing, infinitesimals. He called them infinitesimals, and this he would call a vanishing ratio. That was his term for this whole concept of what's going on at a particular instant in time. And you might ask, well, how small of an instant of time are we talking about? How small is dt? It's very small.
Vanishingly small.
Vanishingly small. And one way to describe it is think of any number you want, as small a number as you want. dt is a little smaller than that. It's almost an imaginary number, but it works. That's the magic of calculus. It works. So, dx, the ratio itself may turn out to be large or small, but it's not always 0. It might be 0, but in this case, it's not. There's a change in x for every little. Oh, and that's the other thing. I always stumble over the word infinitesimal, both lingually and conceptually. So I'm just going to say, when I talk in calculus terms, I'm going to say, well, dt, there's a tiny change in x for a tiny change in t. But when I say tiny, I mean really vanishingly small. Okay, so v equals dx dt, that means we're talking about instantaneous velocity. Now, we could now graph velocity, but it would be kind of boring because it's constant. But we want to think in terms of that. Okay, now the y-axis is v, and we've got a straight line, a straight horizontal line because the velocity is unchanging. But what if the velocity does change? It might look like this. Imagine the car driving down the street, but there's speed bumps every so often. So the car is going to be slowing down and speeding up. It might look like this. So there might be times where it almost comes to a stop, but then it speeds up again, and so on and so forth. What is dx dt? Well, it's constantly changing, but we can still imagine what it is, and here's how we do it. Again, this is just intuitive calculus. Dx dt equals the slope of the curve at any instant in time. And so the way you define the slope is you have to construct a tangent. Now the idea of a tangent line is it touches the curve at one point and only one point. How small is that point? Vanishingly small. It's a tiny. Okay, so you can see I've just approximated the slope just to show it's changing. Sometimes it's almost zero, sometimes it's steep. This would maybe be close to the steepest. And you can graph this velocity, and that's where it gets more interesting. It might look like this. This is your velocity now. Kind of looks like a sine wave. Well, that's because I constructed this little thought experiment that way. And then if we were being precise, we'd have to say if the car was going in the other direction, we'd have to call it a negative change in space and a negative velocity. So we're going to have to deal with positive and negative velocities. But it's all very simple. It's easy for me to say. Okay, in fact, this is a thought experiment. This is a hypothetical plot of the position of the car over time now. And one could be whatever you want. One actually could be 100 yards. You just have to convert it from one to the other. But 1 equals whatever, 100 yards, let's say. And x, the 0 point on the x-axis is just some designated neutral point, so that the car is oscillating in the positive direction and the negative direction. And this is versus time. So it's oscillating in time as well as in space. Oh yeah, don't ask me how the driver is able to produce such a lovely sine wave. He's just a very good driver. The frequency happens to be 1 cycle per minute. That makes things easy. 1 cycle per minute. And we can write a formula for the sine wave as we've done before. In terms of in terms of time, we just say x equals sine times 2 pi ft. And now let's say we want to know the relative velocity at any point in time. Okay. We want to know the velocity at any point in time. And as I showed you earlier, what that means is we have to find dx dt. Now, what I'm doing is I'm condensing a semester's worth of calculus into about 15 minutes. I'm leaving out some details. That's all right, you can trust me. I'll tell you what the answer is. When you have a sine function like this, and you want to take the derivative, in this case dx dt, it's just a rule that you follow. All right, velocity we've already decided is dx dt. What does that equal? Well, what you do is you take this coefficient in front of t. That's the coefficient of t. It's 2 pi f. And you're going to put it down here. And then that's the coefficient of what? Of the same sine function. Except no longer the sine function, it's a cosine function. So that's the thing that changes. But this term here, that's called the argument of the function. So that's all there is. There's a couple of rules to take the derivative to get the velocity. I'm building, because Maxwell, again, I can't leave this topic without making sure you realize the magic of Maxwell's equations in this context. So I appreciate your bearing with me.
So Jeff, just to clarify, when you say derivative, you're talking about a dx dt
yeah.
at a particular point in time on the curve.
Right. So remember what dx dt is. Think of it as simply the slope. And I'm going to show you that in a minute. So when I say take the derivative of this function, you can translate that, find the slope of this curve at different moments in time. Perfect. And it turns out it's a cosine function. And it looks very similar except for this, which again, just to remind you, this would be the amplitude. The amplitude changes, but if you scale the amplitude appropriately, it looks very similar to this function, except look, it's shifted half a cycle to the left. So again, to your point, what am I doing here? Well, oh, right, there's the peak of the, I'm just showing you the peak of the velocity there, some amplitude. But anyway, look at the slope here. The slope here of this function is very steep when it's at the node. When it equals 0, when x is at the 0 point, the slope is very steep. So if we want to represent the slope down here, well, gee, we should put, it's a positive slope, so it's going to be a positive number. It's going to be the maximum amplitude of velocity. If we go forward a little bit, oh, so there we draw the second graph that way. Now let's look at this transition from a positive slope to a negative slope. It's at its maximum point in distance. For that brief moment, the velocity is 0. Well, that means that the graph of our velocity should be 0 there, and it is. And that's the beauty of the cosine function. So I'm showing you why the cosine function basically turns out to be the derivative of the sine function without worrying about too many of the particulars. And the same thing, you can just go on and on. Here's a negative slope, maximum negative slope corresponds to the maximum negative amplitude, and so on. And you can do one more step. You can take a second derivative, you can take a derivative of the velocity, that's acceleration. But for today, just think of the acceleration instead as what we call the second derivative of the position. And here's the rule for taking a second derivative. Oh, this is the notation for a second derivative. You take, again, the coefficient of t, and you put it down here and you square it. And then you bring down this sine function, except you put a negative sign in front of it. And the argument, again, is the same, and there you are. So that's a second derivative. And again, it's a negative, it's just basically the flipping of this sine function vertically. And so now you know about derivatives and second derivatives. Again, teaching you just enough, so now you're ready for Maxwell's equations, because we're going to be playing around with second derivatives, and the speed of light is going to jump out like magic. But that'll be for next week. Any questions at this point? Thanks for your attention. This perhaps will be the most, well, that last part is a little challenging. But as I say, once we get past Maxwell's equation, there's no more calculus. So you only have to remember that calculus for one week. All right. Yeah, question.
Do you have a resource or anything that if you wanted to?
Oh, yeah. Thanks for mentioning that. This material that I've covered today is not really technically part of what they teach you when they teach special relativity, but I wanted to give you the context. And this just comes from a variety of sources. But you can look up Bradley, you can look up Galileo, you know, there's YouTube, there's so much content out there. I don't have any particular reference to mention. I often go to Wikipedia for a start, and then I look at those sources. And you just follow your curiosity. It's kind of it's a wonderful thing. When we get to special relativity itself, I'll have a couple of sources that I use that you might be interested in, but there again, there's lots of sources out on the internet. But I'll give you some more sources when we actually get to special relativity.
Okay, thank you.
Jeff, are you gonna share the PDF at the end of the class or week by week?
Week by week. In
Okay,
fact,
because
so
you can send it.
I'm gonna go home today and tune that up a little bit, kind of clean it up, and I'll send it to you.
I'll send it to the class.
Yeah. Okay. Again, thanks for your attention. I'm just glad that there are other people interested.